Hello and welcome to a new tutorial in your YouTube channel Science and Engineering, and today we continue with electric circuits, the concept of current divider. So for this we have a simple DC circuit with a current source, 2 amps and 2 resistors here, the R1 and the R2. R1 is a constant resistance and R2 would be a variable resistance that would change from between half kilo ohms to 5 kilo ohms. So as we can see in this circuit, the current I total here from this current source will go like this in this branch, and then at this node it will divide into I1 going through the resistor R1, and then I2 in the resistor R2, and then they will join here again this node and come back here. For the purpose of explaining this current divider concept, we have chosen here a current source. Simple explanation about current source, it can be possible that we can also use here a voltage source instead of a current source. So it is not necessarily that if we talk about current divider that we use a current source, and if we talk about voltage divider like we have talked before in the previous tutorial that we should use a voltage source. We can use a voltage source here instead of this current source and explain the concept of current divider. And we can also use a current source in the circuit that we explained before here. That was the voltage divider. We can also use here a current source instead of the voltage source to explain the concept of voltage divider. So just to make it just to clear this point, so we have chosen this ideal current source, as we can see, and this can be also modeled as a transistor, which we will explain later also in the active component circuits when we have a transistor here. So that gives us a constant DC current. So for the time being, we will just focus on the current divider concept. So for this, we have this rule for the current divider that if I'm interested here in the current across this branch, across this resistor here, R2, which is our load here, a variable resistance. So the rule is that the current across this resistor, IR2, is simply given by this formula. It is the R1 divided by the sum of the two resistors R1 and R2 multiplied by the total current. And the way we have derived this equation, we can see it here from these calculations here, that the R total, the sum of the resistors in this circuit, since R1 and R2 are in parallel, so the equivalent or the total resistance can be given by this formula, R1 multiplied by R2 divided by the sum of the two resistors. And the voltage drop across R1 is exactly equal to the voltage drop across the R2, since they are both in parallel, and that would be also equal to the voltage drop, the total voltage drop across the equivalent of these two resistors, the V total. So we say that VR1 is just equal to VR2 equal to V total if we consider the total resistance. The current passing through the resistor I2 is given by Ohm's law. So IR2 is just VR2 or V total divided by R2. And the I total here is also given by Ohm's law. It will be equal to the V total or VR1 or VR2 divided by the total resistance of these two resistance here. So we can find that this will be equal to VT multiplied by the R1 plus R2 divided by R1 plus R2. From these two equations here, if we divide the IR2 divided by the I total, we come to this formula. So the VT will cancel, V total will cancel, and this R2 will cancel with this R2 here, and we come to this formula here. One remark about this formula is it looks pretty similar, or looks similar to the voltage divider formula that we have derived before. So the voltage divider formula was like the V2, the voltage drop across R2 is R2 divided by the sum of the two resistors, R1 plus R2, multiplied by the total voltage drop. Whereas for the current divider, it is R1 divided by the sum of the two resistors multiplied by I total. So the only difference here is that we have substituted the total voltage with the total current, and if we are looking for the current in this branch, in this resistor R2, then we use R1, the opposite resistor, instead of R2. And the denominator will always be the same, R1 plus R2. So this tells us that if we are looking also for the current across R1, so all what we have to do that IR1 will be just equal to, everything here will be the same, but since I'm looking for the current in this R1, then I will use R2 instead of R1. So I always use the opposite resistor value. Again, this equation also is a non-linear equation. So we expect that the changes in the current passing through this resistor will be also non-linear to the changes in the resistor R2. If we look at the schematic that we have here, in the green here we have the current passing through the resistor R1, which is the constant resistor, the 1 kilo ohm that we have, and the red is the current passing through our variable resistor, the R2, or the load that we have. So at the very beginning, when the R2 is very small, with half kilo ohm, and the R1 is 1 kilo ohm, so we have this current value here at R1 and this current value here at R2. If we go to the circuit, just to explain, the current here, the I1 and I2, the current prefers to go to the branch which has less resistance. So the less or the smaller the resistance here in this branch, the more current that will flow in this resistor. And the more the resistance value here in this branch, the less current will flow in this resistance. So this tells us that if we want the maximum current to pass through this resistor R2, or maybe all the current to go in this resistor R2 instead of going through R1, so we have to minimize the value of this R2, and the minimum value will be 0 as a short circuit. So if this is like a short circuit, this means that all the current will go here, nothing will go to this branch R1 because it still has a resistance value here, and all the current will go through this resistance R2, which is 0, a short circuit. And on the other side, if we start increasing the value of this resistance R2 from half kilo ohm, or from 0 to 1 to 2, 3, 4, 5 kilo ohms, then we are getting less current passing through this branch and more current passing through this branch. And this we can see in the simulation. So as we are increasing the value of the R2, then less current is passing through it because it becomes more resistive, and until it goes to 0 if we have an open circuit. And on the other side, when we increase the value of the R2, so the current finds it better or suitable to go through R1, and we get a more current increase in this branch R1. One remark here is that since we have chosen here a current source, an ideal current source here, for the purpose of explanation, so these 2 amps will be at any time divided between these 2 branches. So applying the Kirchhoff current law at this node, the sum of I1 and I2 at any point must be equal to this I total 2 amps, and this we can see also here in our simulation. So if both resistors have the value 1 kilo ohm, so the current will be divided equally between the 2 resistors, and the value of the current will be 1 ampere in each of the 2 resistors. as we change the value of the R2, we get a less current flowing in the R2, but more current in R1. And the sum at any time must be equal to 2 amps, since this is the total current source that we have. Again, you see that the change also here in the R2 is nonlinear, so the change from 1 kilo ohm here to 1.5 kilo ohm here has caused the current to drop in the R2 resistor from 1 amps here to 0.8 amps, so actually 0.2 amps. Whereas if we go forward here at this point, we can see that if a change from 3.5 to a 4 kilo ohms, again half kilo ohm change, only caused a drop from from a 0.45 amps to a 0.4 amps. So it's a small change here. So the big changes occur at the very beginning. It's more sensitive at the beginning and less sensitive at the end. So the curve tends to be more steep here, more flat here at the end, where it is more steep here at the very beginning. The current source here that we have chosen is an ideal current source. We can also use a passive, this is called actually active current source. There's also another type of current source, which is a passive current source, and this is generated by a voltage source and a resistor in series. And this will give us a current that will be also variable, not fixed like this one. For this tutorial, this sums actually what we wanted to explain about the current divider, and the approach here is much more similar to what we have explained in the voltage divider. If you have any questions or any comments, you can just leave it down in the comments below. And until next tutorial, thank you and best luck.